Okay, I think we should be live now. This is going to be a walkthrough of the vehicle detection project. So this is the 5th project of term 1 from the self-driving car program. And I know that many of you are excited to get some help with this project, get some of the tips and tricks that I've been sharing with some of you in the project channels. But what I'm going to do today is basically walk through the pieces that are presented in the lesson. So each of the functions that are presented in the quizzes in the lesson. And then I'll be trying to keep an eye on the questions that are coming in and answering those if they seem relevant to what we're talking about at the very moment. But otherwise, I'm going to scroll back through the questions at the end and try to go through each one and just make sure that everything's clear. So what I'm going to do is basically give you all the pieces that you need to build the basic implementation of the project, and then encourage you to take it from there. So basically, this isn't going to be the entire project, but it's going to be what I think is everything you need to know to get the kind of momentum going. So we'll go through what's in the lesson. I'll add a few pieces on top of that, and by the end, you should have everything you need to know to finish the vehicle detection project. So I'm going to go ahead and share my screen, and that way I'll just sort of step through the code and tell you what I'm doing at each stage. See if this works. Okay, so all right, so what we have here is a notebook where this is kind of just going to be in sandbox mode, like not a polished product, but sort of looking at all the pieces, how they fit together, and then putting them together in the end to get a decent result. So, right, so let's just start over here. So the project repository is this one. It's a lot like some of the other projects. You basically have some description of what's here and what's expected of you, but what we really want you to turn in is a great write-up. So we've got this write-up template. I'll just take a quick look at that first before we get started. And so the write-up template is meant to be basically a starter file for you to fill in the steps you took up for the project and the kind of how you believe that you fulfilled each of the rubric points. We started doing it this way because it seems like in cases in the past where we had a rubric that wasn't maybe clear enough or something, then people were missing rubric points and having to resubmit the project just because something was unclear. So here we actually are including each of the rubric points in the write-up, and you're free to then just fill it in and explain how you did it, what you did, include some images just like this, showing a sort of an example of some of the training data, car, not car, an example of what kind of output you get when you run the hog feature, SK image hog feature function on some of the training data, examples of sliding windows, finding detections in each of the frames, and then making a heat map, and ultimately getting bounding boxes for the vehicles in the frame. So that's just meant to be a starter file, but you should take that and you know, you can use this as your template, or you can kind of write up something similar of your own. You can submit it as a markdown file or as a PDF, just so long as it's something that explains clearly to the reviewer what you did and sort of how you satisfied each of the rubric points. The thing about this project and about the last advanced lane finding project is that they're a little bit less structured than other Udacity projects you might have seen. So this write-up template is important because we're sort of seeing projects come in of all different shapes and sizes, and it's important that reviewers have something to read and follow along with other than just the code. So go ahead, clone the repo, get started with checking out the data, and work on the write-up as you work through the project. So I've got a notebook here that I've gone ahead and put basically each of the pieces. I see there's some questions coming in. I'm gonna just step through this for a while, and then I'll then I'll start to turn back to the questions. I think it might be a little distracting if I go back and forth, but anyway. So this is the setup that you'll have when you download the database of vehicle and non-vehicle images. And so I'm reading in, first of all, just all the images to see how many I've got. And so when I run this cell, I can just go ahead and run each of these. I find I've got 8,792 vehicle images and a similar number of non-vehicle images. So the next cell here, I'm just going to import some of the packages that I'll need, so I can sort of do it all in one place. And then I'll get into defining all the functions I need. So here's a bunch of functions that I'll just sort of go through. All of these are covered in the lesson. So I've just copied and pasted these from the quizzes in the lesson. But we'll go through them one by one just to make sure it's clear what each one of them is doing. So let's start off here with get hog features. So this is just a function that we're going to pass an image to, and then the hog parameters that we've decided on, the number of orientations and pixels per cell, cells per block, and whether or not we want an output image. The viz equals false means we don't want an output image to come out, and feature vector equals true is saying we want to unroll the feature vector. We don't want to get it back as a multi-dimensional array. So like I said, this is just right out of the lesson. We're going to say, okay, if we want an output image, then we'll call this particular version with viz equals true or visualize equals true. And then we'll get back some features and an image that's not exactly equivalent to the feature vector, but it's sort of a visualization of what the hog function is doing. Next, we basically just do it without the image if we want to have only the feature vector come out. So the next thing is a bin spatial function. This is another one defined in the lesson to perform spatial binning on the image. So this is basically just downsampling the image. So the training data are 64 by 64 pixel images, and I've got this sort of default downsampling here to 32 by 32. So you could play with that number and see what works best. This is basically just taking some of the spatial and color information into the feature vector. So this returns stacked feature vector of the 3 color channels having been downsampled to whatever resolution you decide on. And now this color histogram function is to bin up each of the color channels into a histogram. And what you'll notice is different about this one. This is important to catch right here. What's different about this from the lesson is that the one in the lesson has this bins range keyword defaulting to 0 to 256. And I didn't notice this until I started putting this together directly from the lesson, that can screw you up if you are, in this case, we're reading in PNG files instead of JPEGs, and the default range that MP image reads them in at is 0 to 1. So this binning scheme will not work. So I got rid of that altogether. I don't think there's a reason to specify the bin range. You more are just interested in how many bins you want to use for the histogram. So again, we're going to go through and bin up each of the channels, each of the color channels, using the histogram function, and then concatenate those feature vectors together and return the resulting feature vector. So those are kind of the 3 main feature extraction functions we're going to use: this get hog features, bin spatial, and color histogram. And then we'll just define some other functions that are kind of wrapping those in to extract the entire feature vector out of a particular image. So this is another function from the lesson calling extract features. And so this one you can pass in a whole list of file names of images, and then all of the parameters that you want to use to define the feature vector you want to extract. So color space and spatial binning, histogram binning, and hog parameters. And so in this case, this function will step through each of the file names that you pass in the function images and return a feature vector for each one of those, starting off by converting color space if you decide to do that, and then applying each of these feature extraction functions in sequence and appending the resulting feature vector to what we're calling file features, which is just the features for this particular file. And so we'll then do that applying color histogram, and then after that, the hog function, you have to do some if statements here to see if you are asking for a single hog channel or all 3 channels, but basically just passing in those parameters using the functions defined above to extract feature vectors. So at the end of that series of steps, we've appended all of those 3 feature vectors together, and then we're going to just concatenate them and add that or append that to the overall list we're calling features. The important thing to note here is that we added these in the order, in this case, spatial features. So let's see, this particular call right here is appending the spatial features to the current feature vector, then the histogram features, and finally the hog features down here. And what that means is that you've got to do that in the same order when you are extracting features from images that you're trying to classify as car or not car. If you mess with the ordering, your feature vector won't make sense anymore. Your classifier won't register it as, or you basically, your classifier won't work. So you definitely want to pay attention to which way you're doing this. You don't have to do it one particular way versus another, but you should make sure you do it the same order. I've gotten it wrong, and it is pretty frustrating because it suddenly doesn't work, and it's hard to figure out why for a little while. This is another one you've seen, slide window. So this is basically passing in an image, an X and Y start and stop point. So you're identifying a region of interest in the image that you want to consider. And then how big of windows you want to extract or draw on this window, and how much you want the windows to overlap. And so this function is just going to return a list of windows, basically a list of bounding boxes. And so it just steps through asking if you want to delineate the region of the image in X and Y, and then deciding how many windows you can fit in there based on how much they overlap and so on, and giving back a window list. So this is one of the functions that you played with in one of the quizzes. And then draw boxes, which was one of the first functions we introduced in the lesson. It's basically, once you've got a list of bounding boxes or windows, then you can use this function to pass in an image and draw boxes on it. Pretty simple. You can mess with the color or the thickness of the boxes, and then just use the OpenCV function rectangle to draw all the boxes that you passed in. Here's function single image features from the lesson. This is basically just a different version of the extract features function that was seen above. With extract features, we passed in a list of file names. In this case, we're actually just going to pass in an image. And again, the color space, spatial binning, histogram bins, all this stuff, and whether or not you want spatial features, histogram features, and hog features. So all of those things get specified just like in extract features, but this is applying the feature extraction to just a single image. So the reason to have this defined as well is because with extract features, we're going to use that for training when we want to pass in a huge list of training data. And for single image features, we'll use that with extracting features from single windows that we've pulled out of an image and want to classify as car or not car. So this does all the same things. You want to make sure, again, like I said, that you're extracting features in the same order, or rather Doesn't matter which way you extract them, but you got to put them into the feature vector in the same order that you trained with. Otherwise, you'll get some kind of nonsense. And let's see here. So the next function down here is search windows. And so this is now you've got an image that you want to search. You've got windows defined, this windows list that you got from above that you want to search each of the windows. And so you pass in image and windows, and CLF is your classifier. So this is the trained, in this case I'm going to use the linear SVM, which is what we recommend in the lesson, but it's whatever classifier you decided to use. And your scaler. So the scaler is the tool that you use to normalize the data. So basically you should have extracted all the features and then applied the standard scaler function from sklearn to normalize all the data in a per column normalization. And then you apply that same scaler to each of the inference feature vectors, or each of the feature vectors that you extract from the test images. And so again, specify the color space and binning schemes and hog parameters and so on. And then what I'm doing here is creating a list. Again, this is right out of the lesson. So creating a list of windows, which is going to get appended to each time we find a positive prediction. So what we do is we step through each of the windows in the list and extract the window, extract that subregion of the image, and we're resizing it to 64 by 64. The reason for that is because the the training data is all 64 by 64 cutouts. And so in this case, we're going to resize our test window to the same size as the cutouts because we want to extract the same size feature vector. And it just makes things easier if you're passing in an image that's the same size as your training images. Of course, if your test windows were all 64 by 64, you wouldn't need to resize them, but this is just sort of makes it generalized to other window sizes. And then we're going to use that function we defined above, single image features, to extract the feature vector, and that's going to get passed back as this features variable. Will then scale the features using the scaler that we fit using the training data, and then make a prediction based on that set of test features. Okay, so then if the prediction, so in this case, prediction is just applying this CLF, your classifier's predict function on the test features, and if that comes back as a 1, in the case of the SVM I'm using, then that's a positive detection, and I'm going to append to the on windows array so that I know, okay, this window returned a positive detection. And then that's what I'm returning from this function. All the list of windows that were returned as positive detections. Okay, this final function is just for plotting. This is not from the lesson, but this is just something I added to be able to generate a figure for multiple images. So let's see. Enough talking, let's start doing something here. We've now got all of our functions defined, and I'm just going to specify that I want to plot inline, otherwise I won't see any output in the notebook. And what I'm going to do, I've read in my list of car images and not car images into these long lists of file names called cars and not cars. And I will choose a random one of each of them and just plot it up, see what it looks like, and extract features and see what they look like. So in this case, my car image is just going to be whatever random one I pulled out. My not car image is going to be another random one I pulled out. And I'll just start off with the RGB color space, 6 orientation angles for hog with pixels per cell and cells per block set to 8 and 2. Set the hog channel to 0. This means the first color channel will be the one that I extract hog features on. and spatial binning of 16 by 16. So I'm going to take that 64 by 64, downsample it to 16 by 16, and then 16 bins for the histogram. And I'm going to extract features for all 3 spatial histogram and hog features. So I'm going to do that by applying single image features to the 2 test images and then plotting them up. So let's run that cell. Oops. It still worked because I'd already run this cell above, but of course I need to run the cell above to get the functions in, functions defined, and then what we get out is this result. So now we're looking at a car image and its corresponding hog image, and a not car image and its corresponding hog image. So this is kind of just giving you an idea of what the difference is between the feature vector of a car and the feature vector of a not car. So it's useful to look at several of these. You might want to plot up a lot of them actually, because it's interesting to see what, even just visually with your eye, what's the difference between an image of a car passed through the hog feature extractor and the image of something else passed through the feature extractor. And what you can see is that the image of the car actually, even though it's quite rough, does have some pretty distinct features and almost kind of looks like a car in the hog image. And the not car image looks like something else. So let's just do that a few times and get another feel for this. So the idea, if you look into some of the literature on hog classification, is you'd like the relevant sizes in your binning scheme, like the cells, so pixels per cell and cells per block, to have something to do with the size of the things you're trying to detect in the image. So in the case of a car, you've got like the taillights and the bumper and the license plate maybe in the back window. And so if you look at those things in an image that's this size, they're kind of the order a cell size or a couple of cell sizes. And then your block size is also relevant to catch some of the bigger features. But basically, you end up with the rough outline of a car sort of being defined by the hog feature vector that's extracted. So it's fun to look through these. You should definitely like play with the database, and it's something that you should demonstrate that you've done when you turn in your write-up. You had to look at the data and you kind of feel like you know what defines a car from a not car just by looking at some of the features that come out. And it's actually good to look at the histogram binning and the spatial binning as well. I'm not doing that here, but anyhow, moving right along. So now what we want to do is try training a classifier and seeing what kind of features, what kind of parameter settings give the best results. So let's just try that here. So let's first just try RGB. We'll do some messing around here, and then I'll kind of set the settings that I like. So hog channel 0, that's just going to take the first channel and extract hog features there. Spatial binning and histogram bins will stick with 16. I'm going to set it to just do 1,000 samples because it takes a long time to train otherwise. So I've been playing around with this, and later we'll just train on everything. But all right, for this so let's just step through what I'm doing here. I'm setting n samples equals 1,000, and then I'm going to generate 1,000 random indices because I don't want to just pick the first 1,000 in the data set. I might get a different result if I picked, some other 1,000. So I'd like to randomize it and see what I get. The test cars are then going to be, it turns out you have to use a NumPy array of the list to be able to index it like this. It's kind of weird, but so we're going to have 1,000 test cars based on those random indices and 1,000 not cars based on the same indices. The indices in the cars don't correspond to something else in the not cars. They're just a random sample. And then what we're going to do is extract features in a big list for the test cars, and the same features for the test not cars. And then we'll just print out some stuff like how long did it take to compute the features, here we're gonna, this is all stuff that's right out of the lesson. I just copied and pasted here. So this is stacking up the feature vectors. We're gonna stack the cars on top of the not cars. And this is basically just saying, okay, we've got these long lists of feature vectors, and we want each feature vector to represent a row rather in a very large array. And so we just use this NumPy function called vstack, which stacks vertically all of these feature vectors that we passed in. And then we'll convert it to 64 to float 64 so that we don't get screwed up doing some of the math here. And I think actually standard scaler might be expecting float 64. Anyhow, so we're gonna fit a scalar now. So what this means is we're gonna take this large array called x, pass it into the standard scalar function, which is something we extracted from sklearn model selection, I believe. It's worth mentioning too that in the quiz, in the lesson, we used this import statement because in the quiz backend, we've got scikit-learn 0.17, I believe. And so it's a different import statement than you'll use most probably on your home machine, because you probably have scikit-learn 0.18 if you put in the CarND starter kit, if you use the CarND starter kit to get going with Python. So keep that in mind. You'll get some funny message if you try to import this one, and it'll tell you to use the other version. Okay, back to what we were doing. So this definition of y looks a little weird, but it's basically just saying, okay, we want a long array of ones for all the things that were cars in our training set, and a long array of zeros for all the things that were not cars in our training set. And that's just, those are just your labels then. So you've defined a long list or long array of ones where they're cars as your positive labels, and zeros where they're not cars for negative labels. All right, and then we're just going to initialize some random number between 0 and 100 to pass into this function train test split. And I think I was confusing myself there with the standard scaler. I think it's train test split that gives you the weird thing between scikit-learn 0.17, 0.18. Anyhow, it's not gonna be a big deal. You'll just figure it out which version you have if you end up calling the import statement wrong. But here we're just splitting up the all the training data into a training set and a test set. And this might be a little different than what you've done in some of the other projects. You might have had a training, testing, and validation set. The purpose for having 3 sets is basically because you want to iterate in deciding on the definition of your model by training on a particular set of data and testing on another. But ultimately, you want to test the wording gets confusing because some people say validation set for the ultimate set and some say test set. But I think test set is most commonly used for that last data set that you hold out until the very end when you've decided on your final model, and then you test the accuracy on that. We're not going to worry so much about that here, because basically the final validation of your model is whether or not it actually reliably extracts vehicles from the video. So we just want to kind of get a feel here for what parameters make the model perform the best on this test set, this smaller test set extracted from the overall training data set, and then we'll run with it from there and make tweaks to see if we can get it performing better on the actual images and video. All right, so that's that. I'm going to print out some more stuff about what we're doing, how long the feature vector ended up being when we used all those different settings for spatial and histogram and hog features. We'll choose a classifier here, in this case, a linear support vector classifier, linear SVC, and then time, how long it takes to train that, just for fun, and then test the accuracy by running the score function of the classifier after it's been trained. So let's try that. See how it goes. Okay, 7 seconds to compute the features for those first 1,000 cars and not cars. It says you're using 6 orientations, 8 pixels per cell, and so on and so forth. This yields a feature vector of 1,992 elements. It's worth paying attention to how long your feature vector is. If it gets really, really long, things are going to take longer to train and predict on. So you want to try and not be using excessive features. But anyway, this is fine. 2,000 might run as high as 6,000 or 8,000 if you change the parameters. But it took 2.8 seconds to train the SVC, and it's 94% accurate. So for those of you who played with the project, you'll know that even if you're 94% accurate, you're going to have a lot of false positives. And that's just because if you search, if you search 100 windows and you're only right 94% of the time, then you're going to have a handful of false positives. More likely, you'll be searching hundreds of windows with the sliding window scheme that was presented in lessons. So you might have lots and lots of false positives. So we'd like to get this accuracy up higher. And the way to do that is to mess with these parameters and to mess with the color transform. So we've talked about color spaces and how other color spaces can be better at picking out features. RGB turns out to not be that good. So you can play with it, but you probably want to choose one of these other ones. We've seen most of these in the lesson, but I'll choose YCRCB or Y chroma red, chroma blue as the color space without much explanation as to why, but I'll let you just play with these other ones and see what works best for you. This will end up with some sort of strange looking color channels, but they tend to pick up gradients pretty well. The orientations, 6 is probably enough to do okay, but in some of the literature, like if you read the original paper on hog features, they said that they see improvement up to 9 orientations, and then it seems to taper off. You don't need more than that, so we'll go with 9. Pixels per cell and cells per block, I'll leave these at 8 and 2, just because, as we saw in the images, the pixels, 8 pixel cells are kind of the size of the features we're looking for in the images. And then the block size of 2 per block helps with the normalization. So if the lighting is changing or there's shadows and things, then we should still get a consistent result. I'm going to change hog channels to all, because if you play with this, you'll find that extracting features on one channel will give you an okay result, but if you extract features on all channels, you get a significantly better result. So we can go ahead and up these maybe a little bit too. This is going to make our feature vector really long, but suffer through it and hope that we get better accuracy. We'll try this again on another random sample of 1,000 images. I'll just run this cell again. Okay, so now it's taking a little bit longer to compute the features. And we see that the feature vector is now over 8,000 elements long. It's getting quite large, but still manageable if you don't have, if you have a decent laptop, you can still run this project with a feature vector that's that long. Now we're up to 98.5 accuracy. And this is on, remember, just 1/10 of the data. So it's starting to look all right. Rather than play with the parameters all day, I think I'll let you guys mess around with it more. You can tweak things and maybe get a better result, but more or less just going to go through this as a kind of example. What you want to do is decide on some feature vectors and then explain why you did that in the project, because what we're looking for is not just that you kind of went through the steps and got to a result, but that you played around with things and that you understand what you did and you decided on the way you decided on to do it based on some rationale, some experimentation. So if you wanted to get really crazy about this, you could create a pipeline and search a whole grid of parameter space, but that's not required. You can just sort of mess around with these values. What I'm going to do now is just set this to train on the whole data set and maybe take some questions, because that's going to take maybe a little while. Let's see here. So that ought to work. And now I'll just take a look at the questions while that trains. So I'm just going to scroll up to the top. We say, Hola, hello, and hey. People showing up. Denise asks, how much of Project 4 is used in Project 5? Well, some of the things like color spaces that you learned about in Project 4 are useful in Project 5. And if you're going above and beyond, then you can combine Projects 4 and 5. So we've had lots of people turn in their vehicle detection result with the lane finding result and also include it in the video. So that's not required, but you can certainly put Projects 4 and 5 together and make one project. Other than that, it's the same video. So that part is used in Project 5 as well as 4, but other than that, it's basically quite different stuff. Rana asks, my mentor mentioned they should be independent. Okay, that was a response to that, yes. Let's scroll down here. Rana asks, are we using all the folders inside the vehicles folder? Yes, so they're separated that way just because of the way that I collected the data. Some of it was from the GTI database, some of it was extracted from the Kitty database. A lot of the negative images are actually extracted from the project video. That's to make it easier for you guys. It's called hard negative mining. Denise asked, may we get a copy of this notebook? I'm afraid not. Basically everything you've seen up until this point is directly copied and pasted from the lesson. And the other stuff that I'll show you down further, I mean, if you wanna like transcribe it from the video, that's fine. What I worry about putting it out there is that we'll just end up getting a bunch of submissions that kind of literally copy and paste from the notebook. So unfortunately, some people, given the opportunity, will just copy and paste. So we try to at least not promote that. So you'll see all the code here, and you're welcome to copy it down, but I won't actually release the notebook itself. Let's see. Rana asks, why did we have a different function for single image versus list of images for extracting features? Basically, I'm being a little bit clumsy there, defining those two. One could be used inside the other, but just the way they got defined. The reason it's like this in this notebook is because I was copying and pasting from the lesson, and so those two functions exist simultaneously in the lesson. Okay, Carlos is eager to see false positives. We'll get to that. Konstantin asks, is it not important to split training and test data before scaling? Actually, you don't want to do that because you want the same scaling to apply to all of your feature vectors. And so you want to, I mean, I suppose you could scale on the training data and then apply that same scalar to the test data, but in general, I think it's fine to just go ahead and scale everything at once. I'd have to think about that if there's an advantage to one way or the other, but you definitely want to be using the same scalar on both sets of data. Whether or not you train the scalar on only the training data may be up for debate. Let's see. All right, well, let's get back to the notebook. We'll get back into the questions in a moment. But all right, so we trained on all the data, took 110 seconds. We've got feature vectors that are quite long and 45 seconds to train the classifier, and it's running at close to 99% accuracy now, okay? That's nice. So now I'm gonna test this classifier on some examples. And these are, I'm not sure if the exact same examples that are in the repo, but they're similar. Some of them are the same, I think. I've got 8 examples. I'll step through what I'm gonna do here. I'm just gonna extract these 8 images that I've got saved here. And I'm gonna define, for now I'm not defining a range in Y that I'm interested in, but later we'll restrict this. I'll just go through the example of not restricting Y. We're going to have these windows overlap by 50%, 0.5, and then we're just going to step through each image. For each image in our example images, we will read it in, make a copy to draw on, convert it to float 32 and divide by 255. So this is important in this case because we are now reading in JPEGs and we trained on PNGs. So this has been a source of pain for some students that it's kind of unavoidable because the way it works with different image reading packages and different image file types and different color conversions and other things is that your images will be scaled on a variety of different ranges, sometimes 0 to 1, sometimes some negative number to positive number, 0 to 255. The other thing is that if you're reading in images, in many cases, you'll get them back as 8-bit or 8 bits per channel, which if you start doing math on those, you end up getting some crazy results. So it's really important, even if this is a painful point, it's important to maybe go through the pain because if you aren't careful about doing your math and floating point and having all your images scaled the same way, then you'll run into this problem down the road if you don't have it here. So that's the takeaway message there. In this case, I know that my PNGs were scaled 0 to 1, so I know these JPEGs are getting read in 0 to 255, so I'm just going to divide. And I print that out just to see that. But anyway, now we're going to use the functions that we defined above to get a list of windows based on our windows, the window selection parameters that we defined above. I'm going to go with 128 by 128 windows, and then return this array of hot windows where the search window function tells me that the classifier thinks there is a car there. So nothing special there, just using the functions that we defined above. And then we'll create this window image, which is going to be drawing the boxes that we found onto our copy of the image, and then we're going to have a look at those. So we'll also print out how long it's taking us to process each image, and then visualize the results. So let's see. Let's run that. All right. So we're running at about 1 point something seconds per image, and over here you can see we're currently searching 190 windows. So it's pretty slow, and that's not that many windows. So what you'll find is that if you search a ton of windows, things get pretty slow. Let's look at the results here. So we're finding some cars, finding some things that aren't cars that we think are cars. Again, found this car okay, but we've got some detections up in the treetops over here. Finding some cars and some guardrails. Wow, this tree is very much looking like a car. I've got more detections in the tree than I do on the cars. And fortunately over here there's nothing where there are no cars. But obviously we've got some false positives and we need to deal with that. So as mentioned in the lesson, one of the easy steps is to just restrict the area of the image that you're looking at. So we don't need to look in the treetops or in the sky because we won't find cars there, hopefully. So let's just restrict the area we're looking at to be, so down here you can see on the y-axis we've got maybe the cars are up to about 400 starting from the bottom, and since I'm going to go with multiples of 64 as my window size, we can go maybe down to 656. 256 is 4 times 64, so let's do that. So 400 in our start and 656 as y stop, and run that. Okay, well it's a lot faster now, half a second maybe per image, because we basically cut the number of windows in half. And we look at the results. We're still missing cars up here. We seem to have missed more this time with this particular search scheme. It just may be the way the windows are laid out, but the other thing you want to do is try different window sizes and different overlap schemes and see kind of what works best. Let's try, for example, 64 by 64 windows. Just see how that goes. And of course, that's going to make our total number of windows quite a bit higher, slow us down quite a bit. So now we're searching 273 windows. It's taking like 2 seconds per image, quite slow. Not exactly the kind of thing you want to sit through 30 frames a second for a 50-second video that the project is based on. But let's just see what the result looks like. Okay. Well, we found this car that we were missing before. We seem to be missing the larger vehicles now. Catching pieces of these and some of the smaller car detections. But so this kind of get to the point of, you might probably want to search several different scales. Maybe only 2 different scales, but at least 2 different scales. We can try searching in the middle as well. Like 96 is halfway between 64 and 128, and that's sort of maybe a happy medium between window sizes and the size of the cars on the road. Now we're around a little bit less than a second, 100 windows per search frame. And okay, we're doing all right. Finding some cars, not too many false positives. In fact, it doesn't look like there's any false positives. So all right, 96 is a nice middle ground, but maybe you want to search down to 64, and maybe you want to search all the way up to 128 or something like that. It's nice to have your search windows be, the size of your search windows be integer multiples of your cell size for hog, because as you noticed, we're still moving really slow here. We're searching just 100 windows, and it's taking the better part of a second to classify all the frames that we want to classify. So now I'm going to get to the step that's of great interest to many of you who've been playing with the project, and will be of interest to those of you who are just getting into the project as soon as you have a very slow pipeline to work with. And that's the step of taking the hog features for the entire image once, and then subsampling that array to extract features for each window. So this is a new piece of code here where I'm just going to step through each little bit and let you know what's going on. But basically that's what we're going to do here. Rather than like up here, we were extracting each sub-image and calculating the hog features for that image. In this case, we're going to calculate the hog features for the entire region of interest that we want to sample, and then go ahead and subsample that array rather than recomputing hog every time we have a new image. Right, so just defining my Y starts and stops. This, by the way, up here is just another, I'm going to use this to convert individual images, because rather than presenting this next piece in a bunch of, with the functions that were defined above, I'm going to make it a little bit more explicit and kind of, hopefully it'll be a little bit more clear what's going on. But I'm not going to have everything buried in nested functions and everything. It's going to be kind of a line by line example. So that's just to convert color space. And I'm going to run that cell so that we have that function available. Right, so this scale now, this is another thing. We're gonna consider this region of the image from Y of 400 to Y of 656, and we're not going to restrict the X dimension. Right now I'm setting a scale of 1, and what that means is this is kind of another trick for searching different window sizes. So rather than take each window, like a 128 by 128 window, and downsize it to a 64 by 64, what we'll do instead is we'll scale the entire image, apply hog to the entire image, and then subsample that array. And the effect will be to be sampling at a different window size. All right, I'll show you how that works. So, right, we read in an image and make a copy just like before. We're gonna do a whole bunch of stuff with this particular cell. This is the heat map stuff that is in the lesson, but we're gonna introduce that now as well. So what we want to do with each positive detection is add heat to our heat map, and then we'll see how we can extract overlapping bounding boxes for overlapping detections. So we got a heat map that's just zeros like the first channel of our image. And then we convert the image again to float and 0 to 1. And now this, what I'm calling image to search, is just going to be a cropped version of the image, Y start to Y stop, and no restrictions in X. What I'm calling C trans to search is just the color transformed image. Again, I'm converting to this YCRCB channel or space. So then if scale is not equal to 1, I'm going to convert that image to a different size. All right. So basically, this is kind of the tricky part, maybe conceptually, but what we're doing here is saying, okay, if we want to do this at a different scale, then rather than select different window sizes, we're actually going to just resize the whole image. And then we'll sample that image at our same window size, and it'll effectively be a different search window. Okay, so peel out the 3 color channels within that transformed image. And then we're going to define what I'm calling NX blocks and NY blocks. And these are basically just, these are going to hold the number of cells, of hog cells, so that, again, we defined our cells as 8 pixels. So how many cells across the image is this particular image? So, all right, we're dividing just to pick the channel 1 shape and divide by pixels per cell, both X and Y dimensions. And then how many features per block are we going to be extracting? And that's just this, the orientation is times cells per block squared. Our window size is 64. That's just the size of the original feature vectors or windows we were extracting feature vectors from. Number of blocks per window is the window size over pixels per cell. The reason I'm using this this division is basically if you divide these with a single regular division operator, you can end up with you're going to end up with floating points, and what we're going to use these for is indices. So we want to make sure that they come out as integers. We don't really care if they're not exactly, if we're not exactly ending up with integer output, but we'd like them to be int data type. All right, getting mired in the details here. Cells per step equals 2. So what this is kind of interesting. Instead of defining an overlap, like 0.5 overlap between windows, I'm saying how many cells do I want to step across the hog array per window step. So in this case, I'm saying 2 cells, which if you remember, 64 by 64 means our grid is 8 cells by 8 cells. So we're going to essentially have 75% overlap between windows. Okay, NX steps and NY steps is asking basically how many steps are we going to make across the hog array to extract features. Right, so you got all that. Now we want to extract hog features for each of the channels. I'm just doing this one at a time here to be explicit that we're going to extract 3 sets of features, 1 for each of the channels, and then let's see. We've defined NX steps and NY steps, so we're going to step through our X and Y positions within the array of hog features here. Notice I'm calling the get hog features with feature vector equals false. So what we're getting out now is a multidimensional array that we can sample from. All right, so here's where we extract hog features for just the piece of the image we're interested in, and we're using this function numpy ravel to unroll each of those feature vectors, and then we're going to stack them up into one long hog feature vector that should look approximately like what we were extracting from individual images before. Some people have noticed that when you do this, you don't get back the exact same result as if you had extracted sub-images and run hog on them individually. This is true because if you extract sub-images, there are discontinuities at the edges of the images, and so that gives you a different gradient than if you extract for the entire image and subsample it. Turns out they're close enough that this still works. You will get more false positives this way, but it's manageable in the overall scheme of things, and it's much faster. Right, so X left and Y top, these are just defining where are we in pixel space on the image for this particular cell, so that if we want to draw it, or rather, in this case, we're going to extract the subimage to do spatial features and histogram features next. So we do those things using the functions that we defined before. And then, as I said, you want to stack those features in the same order that you were stacking them when you extracted features from the training set. So here you have it. We did spatial, hist, and then hog features. So we'll do it the same way. And what we're doing is applying that same scalar to that feature vector to test whether or not our, we're going to pass it to our classifier and predict whether or not there's a car there. If the test prediction is true, then we want to draw a box, and we also want to add heat to the heat map. So that's basically what's going on here. These all get multiplied by scale because where I'm going to draw the box has to do with what scale I'm interpreting the image on. All right, so that basically is just some long, complicated way to draw a box in the place that I want to draw a box. And I'm saving these image boxes for some reason and adding heat to the heat map. So basically I'm saying, okay, within that box that I think I found a car, let's add +1. Right, and then we're just appending these images so we can look at them, and then there's a visualization. So let's finally do this. Let's see what happens. Nothing happens. Oh. It's really slow for some reason. Okay, we're searching 912 boxes. So let's, so if you remember before, it was taking a fair bit longer, but these are, so I'm searching at the smallest size right now, but basically we're getting a pretty decent result with searching 64 by 64 windows. Here's the positive detections, and over here is the resulting heat map. And you can see that for the various test images. So it's working out pretty well. Let me just scale that up to, say, 1.5. Let's see. So, all right. This was running faster for me earlier. I think my computer's struggling a little bit to do the live stream and everything else. But anyway, you can see we do all right at a scale of 1.5 as well. Maybe even better. There we got a false positive. Okay. There we got a false positive. What you're seeing here on the right-hand side is the heat map that we're generating. And so this is the important part about how you're going to get overlapping detections to become one detection. So we've got these hot spots in the heat map. Sometimes we've got a false positive creating another hotspot. But basically, you want to play with the window size and different parameters and things to see what works best. And again, you probably want to like wrap all this in a function and pass it at different window sizes and try to see what you can get away with. If you end up searching thousands of windows, it's going to be a really slow process. You'd like to keep it down to maybe just a few hundred windows, or under 1,000, say. So here I'm searching at 128 missing the smaller cars, but still finding the bigger cars. Right, so that's one of the tricky steps that hasn't made it into the lesson yet, but probably should. I do have a little note in there about, yes, you should compute hog features for the whole image and then just subsample it, but that seems to be not very clear. So anyway, there you have it. And what we'll do next is extract, let's see. So we'll actually do what I said we should do. We'll wrap that in a function. We'll call it find cars, okay? So basically we're just gonna do all of the same thing here. And we're gonna just return the image in the heat map. Right, and so then we're gonna get to the combination of overlapping bounding boxes, which is one of the lessons or one of the concepts in the lesson where we define these other functions, apply threshold to the heat map. This is basically saying we're gonna select pixels within the heat map that are above some value. This means, say if you set it to 2, that means that pixel has actually been detected within the positive detection window twice. And then draw labeled boxes is in order to draw bounding boxes where your label function returned distinct objects. So some of you who were working on this project early on may have noticed that a while back I was playing around with doing blob detection and watershed identification of contiguous regions of pixels and all sorts of messy stuff. But there's a great function from SK image, is it? Yeah, no, from SciPy. This import label from ND image measurements. This function will take your thresholded heat map and return a label, or return labels for where the individual contiguous groups of pixels are. So you can play around with that. This is just a function. These functions are just copied from the lesson. And so now we've kind of got this all packaged into a smaller area here. We'll set the same Y start and stops. We'll go ahead and set scale to 1.5. And then just step through those same example images. We will read them in, use the find cars function that we defined up above, use labels to label the heat map, and then use the function above, draw labeled boxes to use those labels and draw boxes around the areas that are labeled. And then we will take a look at the result. So let's do that. Uh-oh. Find cars not defined. I gotta run the box or run the cell above here. That includes find cars so that I can use that function. And I need to run this one. Okay. So that's gonna take a little bit because each one of those takes a half a second or so. Okay, that worked. So now we've combined all those overlapping detections that you saw into single bounding boxes, right? So we got a nice single bounding box for that car and for that car and for each of these cars. And what you'll see is we also have a bounding box over here for the false positive because we didn't set a threshold on our heat map. So we're basically just drawing bounding boxes around anything that got detected. So again, here we have a false positive. But you can use that threshold heat map function to set a threshold. And what you want to do, I'll just say it right now, I'll probably say it again in a little bit, but what you want to do is not just process this heat map for each individual frame. I mean, it works nicely to test on test images like this. You can see you get a pretty decent result. But what you really want to do in the project is integrate that heat map over several frames, like maybe 5 or even 10 frames. And then the cars should stand out brightly against a background of maybe a few false positives. And you can then threshold that and get a nice clean bounding box around things that are actually cars and reject all the false positives. So mess around with that. What you can do if you have, like in the lesson, I use a series of images and threshold the heat map after adding them all together. And that works nicely. So that's what you want to do. Right, so let's try it on a video, right? That's the whole goal of the project. We think we know what we're doing now. We're going to define this process image function, which we're just going to run the same things, find cars, label, and draw bounding boxes where those cars are, and then return that image that's been drawn on. And we will run that through our video file clip MoviePy tool. And actually, okay, I didn't mean to run that on the entire project video, but what you want to do, I have commented out here, test video is available in the repository, and you should play around with that before you run on the full project video, because as you can see, even though running at like a little better than a frame a second, it's going to take a while to run that whole video. So what I'll do now is just look again back to the questions and hopefully answer some questions while this thing runs for maybe 10 minutes or whatever. Right. Okay, I think I left off with Rana's question. Accuracy got really bad, down to 1%. Any advice on why that would happen? Something's going very wrong there. So yeah, Vivek said check the file format. Yeah, you play around with making sure your images are scaled correctly and so on and so forth. But yeah, 1%'s that's definitely a problem there. When you see 100%, okay. When you see 100% accuracy on test data but low accuracy on images from the road, does it indicate that you need different input data, perhaps image where the car isn't centered? Again, that's probably a scaling issue. What you've seen here is just trained on the data from the database that's provided with the project and have relatively good results. You might have to play with the parameters that you're choosing or the number of channels you're putting through the hog function. How can I limit the maximum number of windows that I search for? Yeah, so you've just got to play around with it. The maximum number of windows, like I said, you should probably try to keep it in the several hundreds maximum. Otherwise, things get too slow. So I've seen some projects come in where they're searching 5,000 windows, and it's just going to take forever. But so play around with how little overlap you can get away with, and how few windows and how many. Like you don't want to have 10 different sizes. Maybe 2 or 3 different sizes is enough. I'm only using one size here, so just for the example, but you probably want to use at least 2. Okay, let's see. Does the Udacity data have cutout images as well as B-box annotation? Yes. If you look at the Udacity data, which is not the data that I'm using for this, but there's actually annotated data provided by Udacity. There's a link to it in the repo. The data there are images, whole images where the bounding boxes are annotated for cars and other things, but you have to open up the CSV file that comes with it and extract the bounding boxes. Let's see here. So anyway, you have to extract bounding boxes from the CSV file. It's a little bit more complex, but okay. Do using rectangular, not square window size help in getting more snug fit bounding boxes around cars? Not necessarily. If you use square bounding boxes, then you're generally going to get a good fit by having many overlapping detections. And so basically you can try different shaped windows, but you won't necessarily get a better result with rectangular windows. All right, hang on one second. I'm going to be right back with you. All right. Slowly processing the video. I think it goes about twice as fast when I'm running this and not running a live stream at the same time. But anyhow, we have plenty of questions to answer, so we'll just keep going through these. I've been getting errors when trying to use all for hog channels on the full image data set. I'm only able to set it to all for a sample of around 200 images. Is there a way around this? I'm not sure what the problem is there. That's yeah, I'm not sure what's going on there. And then Constantine says, yes, that's what I meant. Scale on training and apply to all. Okay. Can you go over taking the hog of the entire image? Do the sliding windows size have multiple hog pixels per cell? Hopefully that got answered, because that's what we went over in the find cards function. Denise says, are all of the vehicle, non-vehicle images in PNG format? Yes, they are. But be careful if you use the Udacity data. I'm not sure if it's PNG or something else. Carlos says, I ended up converting all the training images to JPEG. Not sure if I actually did something wrong there. There's nothing wrong with that. It's just the takeaway message is you have to be consistent in your scaling of images. Otherwise, you'll get problems. Should we play with stop values that are up to the horizon on the image? Yeah, that sounds good. I chose 400 here as the Y cutoff. You could mess around with that. Carlos asks, I think I missed it, but when you use window sizes in multiples of 64, is it because the car, not car images are that size? Not necessarily. I'm using 64 just because that's the way the training data are set up. So I could use other scales. It's not required that I use 64 by 64, but I just kind of chose that as the default scale because the training data are that size. Okay, Constantine says, should windows correspond to each car size? So you shouldn't care about overlaps between windows of different sizes because they're likely correspond to different cars, one close, one far. In fact, you'll find that sometimes you detect the same car at different scales. So I would say for this, there are some vehicle detection applications that try to track vehicles that are obscured, like one vehicle is sort of halfway behind the other one, and that would be a tricky situation, but we're not really asking you to do that here. So I would say if you've got overlapping bounding boxes, you can just count them as one vehicle. Okay, it says, can you mention again what your scale variable is doing? So scale is scaling the image, basically downsampling the image by that factor, by the scale factor. So if scale is 2, then I am reducing the resolution of the image by a factor of 2 in X and Y. And effectively, when I take a 64 by 64 window out of that scaled image, I'm actually sampling a 128 by 128 window of the original image. So hopefully that makes sense. Carlos asked, do you do anything to cool down the heat map between frames? No, in fact, this isn't explained. This isn't explained in the code, and it's a good point. I should probably add something like this to the lesson, but yeah, you basically want to only integrate your heat map for 5 or 10 frames, and then not be retaining the information from 30 frames ago in your current heat map. So there's a few different ways of doing that. You could either, in each frame, you can either add heat where their bounding boxes are, where they're positive predictions, and subtract it everywhere else with a 0 as a floor, so you don't want negative values. Or you can just set it up so that you retain the last 5 or 10 heat maps and sum them each time you want to make predictions, but basically keep just the last 5 or 10. So there's a few ways you can do that, but yeah, essentially you don't want to retain detections that were from a long time ago. That's the idea. Question from Sarvesh. The additional Udacity data, can we use it? Yes, of course, for sure. Does it have cutout images? No. So that's the thing about the Udacity data. It's just got a CSV file that tells you where the cars are, and you have to go and cut them out yourself. A little bit of a pain, but you guys can thank me. I did that to the kitty data, so that's why you have such a nice kitty subsample there. Let's see. JPEG conversion and window size. Okay, got it, great. Could we try deep learning on this project and do it differently from the requirement? I've been saying, yes, you can do that, and I will handle your submission. It's turning out to be a little bit of a pain for the reviewers, so I may have to, for now, I'm going to continue to say yes. We've been handling a few deep learning submissions, and they're great. I really love seeing people tackling this project in different ways. It's just really cool to see. But in general, we aren't set up for that in terms of reviews. So the reviewers, if it just went through the normal channels, might send it back because it doesn't meet the official rubric points. But I've been talking to the student services about that, and hopefully we can kind of figure out a way to do it either way, because of course you guys studied deep learning, and now we're using these more traditional techniques, which some people think is kind of lame, but it turns out a lot of actual automakers are still using older techniques. So they in speaking to our hiring partners, they have been supportive and enthusiastic about us teaching these more traditional techniques as well. So ping me if you want to submit a deep learning version. Better yet, do it both ways. I might end up having to start saying do it both ways to everyone, because if I can't get reviewers to handle either one, then I might have to do it both ways. But some people have done it both ways and enjoyed it, so I recommend it. Right, so let's see. Backing up a little bit. Denise asks, how did you get rid of the false detection in the example with 2 cars and 3 detections? There was a different colored heat map for the false detection. Did that help get rid of it? Do not remember seeing the false detection removed. So yeah, I'm not doing anything to remove false positives. I'm actually just including them. So this is just a very rough and quick implementation meant to give you all the basics. But yeah, what you want to do is something like I was saying, add up the heat map over, say, the last 5 detections, or over 10 frames or something, and add those together and threshold it. So by threshold, I mean require that pixels have greater than some value, and then you will get rid of those random detections in a heat map, and that's one way of doing it. So okay, so let's see. To remove false detections but still get the edges of cars where there are fewer overlaps, how do you handle that? Well, what you'll find is that the detections you get often kind of bounce around the edges of the cars, and if you have enough detections on one car, you'll get a nice bounding box. So that's why it's good to integrate the heat map over. It's another reason to integrate the heat map over several detections. The other reason is that you'll get smoother bounding boxes, but what you can also do is to just add, well, there are various things you can do to try and smooth out the bounding boxes, but mostly has to do with averaging over time. So averaging the position of the bounding box over time and integrating the heat map over time. Okay, so Carlos says using a DQ with max length equals 5 to average heat maps. That sounds great. Sarvesh says, is there an example of using multiple size scaled windows and combining the results? Yeah, so in this case, I sort of changed scales a couple times from scale of 1 to 2 to 1.5. What you could do in your own implementation is just do it once at scale of 2 and once at scale of 1 or something else, and then just add all that. I'll add all those detections to the same heat map. In this case, I'm just doing one size. So we'll break for a moment on questions. Look like we answered all those, and now the video is finally done, and I can take a look at it here. Right, so we'll see how we did. So this is removing no false positives. So all the detections we found should show up in this map. See them popping in here and there. And I'm tracking that car decently. You can see the bounding box jumping around like that. So that's what I was saying about averaging over time. If you average that bounding box position over time, then new detections won't make it jump around like that. And you can also retain it when it disappears for a certain single frame for some reason. Now we're getting one bounding box for both cars because they're overlapping and they separate again. This is cutting off part of the video. Saw some false positives when we went through the shadows there. But basically, this is almost looking like a decent result. You know, we got a lot of false positives, but now you know how to threshold the heat map and get rid of those. And using the same techniques of averaging over time, you can smooth out the bounding boxes as well. So I just want to mention that one way to do this is by introducing a class. In this case, this is the way I did it. I just said, okay, I'm going to introduce a vehicle class and have a bunch of parameters. Is this vehicle detected? How many detections? Or, you know, you can add up how many times have I not seen this recently. The pixel values, so like where you found it. You could add whatever parameters you want here, like best fit or width and height, and then maintain those values over time and either average over frames or kick out the oldest detections and only retain the newest ones. Anyway, it's something you can play around with. It's just like what we did with the line class in the advanced lane finding project. You maintain the position of the lines and you smooth over time. That gives you a smoother result. Same thing here. Basically want to just average detections over time and bounding boxes over time and whatever other parameters. So basically, the way I implemented this, I'm just saying here, I come up with a list, or I define a list called cars list, and then what I can do is just you know, if I feel like if I find I've detected a car, I can just say cars list. Oops, spell today. Cars list. Append. Vehicle. Right. So I put the new car in the cars list, and then I can just reference that vehicle by index in the list. I can take the length of the list to know how many vehicles I have detected in my current frame, and go from there. So let's see. Let's see, one more question here. Says, I want to see the video. How many reviewers are ready for Project 5? The average time for response has been a little high. Yes, part of the problem there has been that a lot of reviewers are certified to review various projects, and so they are, because this one's new and it's a little trickier than some of the other ones, they're defaulting to review other projects instead of this one. We're trying to get more people on board and kind of even things out so that we don't have this problem. But right now, let's see, I think I can take a quick look and see what the backlog looks like. Give me 1 second here. And right, so today is February 10th. Yeah, it looks like it's getting down around 24 hours, give or take. So it's getting better. We really don't want to hold you guys up and make you wait too long on these. We really would like to be turning these around in a matter of hours, not days. But because this is the first cohort and because we're training up reviewers on the fly here, the process is a little bit slow. And of course, coming to the end here, everyone's submitting their projects all at once. But really excited to see you guys submitting the projects. A lot of great results coming in. And you've still got time to submit, even to iterate, and to come up with a great solution. So what I've what I've shown you here is not the whole solution. As you can see, it basically works, but what you'd like to do is try, there's actually a rubric point about reducing false positives, and what you'd like to do is use that heat map method or something like it to get rid of spurious detections, basically where a false positive pops up in one frame and then disappears. If you have a false positive appearing in the same place in many, many frames in a row, then you're going to end up drawing a bounding box around it, and it's probably more of a problem with your feature vector or some other aspect of how you train the classifier. But you should be able to come up with basically fairly smooth bounding boxes around just the cars and no false positives. If you've got, so that said, if your bounding boxes are a little jumpy and you've got some false positives, it's not the end of the world. We're asking the reviewers to be, the reviewers mainly are looking to see that you've understood the project, that you understand the implementation that you put together, and that you kind of thought about it and decided why you want to do things one way versus another. But other than that, you know, we're not going for perfection here. This is more just to get some experience with this kind of stuff. So that's about it, folks. And I'm sure after an hour and a half, everybody's ready to call it quits. But you can ping me if you have any other pressing questions. But otherwise, I think we're going to end the live stream here. And I hope you enjoyed it. And I hope you took away some useful tidbits for your project.